Hey, Intro Engineering Design folks, let me put this slideshow on. I didn't make enough room over here. I want to talk today about material properties. And if you saw the bell work earlier this week, you know that I was asking you all about what do you already know about it. Some people, nothing. Some people, they've Googled stuff and they answered stuff like that. And okay. But material properties and sort of what's stuff made of. So for material sciences and material engineering, you're connecting the science of the material, like the chemistry and the physical properties of material, to the real world products people are using. And you consider the structure and the properties and how you process it. So I want to talk about metals. Metals in general, they're opaque, you can't see through them. They're fusible, so you can melt them together. Ductile, they're conductive, they conduct electricity and heat. And they're typically lustrous, that means they're shiny. So they're good conductors. Some metals are monatomic. Monatomic means like copper just has copper atoms in it, the same one type of atom. Silver just has silver atoms. Gold just has gold atoms, and then of course there's purity issues in some of these things, but that's what that metal is made of. Other metals are alloys of other types of metal. Like there's nickel in a lot of things. There, aluminum alloys. Steel is iron and carbon, and usually other metals to help make certain properties for that steel. Some metals are ferrous. Ferrous coming from the word for iron in Latin, and probably Greek as well, if I think about it. And it's just there's iron in the metal, some amount of iron. And ferrous metals are magnetic, and you can use them in motors and electronic components, which is really cool. And non-ferrous metals, they don't really have anything in common besides the fact that they have no iron in them, and they're not going to rust because they have no iron. Iron, when exposed to air, it oxidizes and it turns, you see rusted things all the time. It sort of starts breaking down, turning into rust. Otherwise, there's nothing really that they share in common besides the fact that they don't rust and they don't have iron in them. Ceramics, they are things that are manufactured or come out of the ground usually. So you got earthenware, porcelain, brick, cement, glass, those sorts of things. Usually it's a non-metallic mineral like clay, and you fire it at a high temperature. These materials are very good at high temperatures. They're really good for high temperature applications. They are not organic. They are not metallic. They are not conductive. And I've already said includes clay, glass, and cement. Cool. Polymers are numerous. There's numerous natural and synthetic versions. They're compounds. They usually have very high molecular weight, and they have up to millions of repeated linked units. Each of those units is a relatively light and simple molecule. And you'll see a lot of the time, these are plastics. A lot of the time you see them in plastics. You'll see people who break down the plastics and they get these long, it sticks together when you pick it up. It's gooey. I should find some videos to put up because they're cool. So they're organic. They have carbon and hydrogen in them, usually derivatives of carbon and hydrogen. And they're low density. They're usually flexible and they insulate. Then you can have composites, which are combinations of two or more materials. Usually you take two things with different properties and put them together so that you'll get kind of some of each of the different materials' properties together in one material. Within the material, the composite material, you can easily tell the difference between stuff. It's not like when you dissolve like sugar in water, you can't really see the sugar particles anymore. But if you stir in sand into water, you can see the sand particles floating around until they settle. So yeah, when you have a composite, you can tell what parts of it are which. They don't blend together and dissolve together. They're not a solution. They're not in solution together. And there's also biomaterials. Biomaterials are either natural or they're synthetic. And you can use metals and polymers. Basically what it's for is for introducing into living tissue. So if you have an implant you're going to put in, replacement knees, replacement hearts, artificial valves, artificial anything you put in the body. If you grow a new trachea for someone, you put it inside, that's a biomaterial. Artificial joints, pacemakers, things like that. Stuff that where you put it in the body, your body's not going to start rejecting it immediately and forming a calcified thing around it so that it doesn't work anymore. Because, the body knows. The body's like, hey, that's weird. That's not supposed to be here. So biomaterials are things that your body will actually accept as part of the body. All right, so science versus engineering. Materials scientists, they're usually people who talk about and think about how the structure of a material relates to its properties. And material engineers are the kind of people who are putting new materials together and taking these materials and making products with them, using them for engineering applications. Your structure changes based on how a material is processed usually. Your structure impacts the material properties and the performance of the item, of the substance. If you consider like diamonds versus graphite, they're both made of mostly carbon, but a diamond and a graphite are very, very different. One of them is clear, one of them is very hard, one of them is not so hard, one of them is soft. You can write with it, you can drag it along a piece of paper, and parts of it will come off and attach to the paper, so you can write things down. Very different materials made from the same kind of atoms, elemental. You've got crystalline solids, and that's a structure where you have very regular, repeated arrangement of your molecules or your atoms. Sometimes that's because they're all tightly packed and they all sort of sit nicely together. Like if you see like hexagons in a beehive, you see the hexagon shape, it sort of tessellates, it sits together. That's one way you could have it happen. Sometimes it's a factor of the molecular structure, like when water freezes and turns to ice, the way that all the little molecules line up is very structured. And that's why you get this ice crystal as opposed to just flowing water. An amorphous solid, on the other hand, that's something where the molecules or the ions or the atoms are just kind of random. They're kind of no real order or structure to them. And then the thing that we're going to talk about, and hopefully I'll get the materials in and we can actually do it in class and maybe even show you guys at home what to do. Density. I want to talk about density. Density is a property of matter where the size of your sample does not change the value of its density. If I have a very large sample of something and a very small sample of the same exact material, they have the same density. And it's related to how much mass there is, how much matter there is in the volume it takes up. So it's mass per volume, or mass divided by volume. And your units are usually grams per milliliter or kilograms per liter. You might have grams per cubic centimeter, something like that. Milliliters and liters and cubic centimeters, those are all units of volume. So mass has to do with the amount of material in the sample. It's related to your elements involved. It's related to the amount of protons and neutrons that you have in your actual atoms. And so something like hydrogen, which has one proton, one neutron, it's a very light, it's not very dense. So, but you have something like like gold or something like that, it's going to be a lot more dense. It has more mass in a smaller sample. Let's see. If you have more of a substance, it has more mass than if you have a small amount of that substance. That's something we know about. I want to mention right now, because I say this word mass and I realize I don't know if I've introduced what mass is besides the amount of matter. Mass is very similar on Earth. It's very similar to the weight of something. So you can use a scale or a balance and set it up, and it will tell you how many kilograms or grams that sample has. It's not the same thing as weight. Weight has to do with how the mass and how the gravity interact. So if you're on the moon, you have the same amount of matter inside your body, but it weighs less because the gravity on the moon is lower, smaller amount. So that's what the difference is between mass. Mass is how much stuff, and weight is how the gravity is pulling down on you. Density is going to be the same, though, no matter how much of a sample you have. I've already said that. I don't know why I have it on another slide. And I should have put the weight and mass thing somewhere. Oh, weight and mass are similar. We use what we know about Earth's gravity. I forgot I put this slide in. Cool. We use what we know about Earth's gravity, and we measure what the mass of an object is by weighing it. I put that in quotes because it's not really. It's similar. Oh, that's about my cue to go. It's usually measured in grams or kilograms. The last thing I think I have is talking about volume. Volume is the amount of physical space that a sample takes up. You've done probably volume equations for geometry before, like 3D figures, like what's the volume of a sphere, the volume of a cylinder, the volume of a box, a right rectangular prism, a cube. We measure volume with water displacement sometimes. Hopefully I'll have the stuff for that soon. And a milliliter of water takes up 1 cubic centimeter. That's why a milliliter and a cubic centimeter, those are like the same, they're volume units. And density is mass divided by volume. I'm going to pause the lecture here. I'm going to come back and I'm going to record about, there's going to be like a little paper to fill in some answers on. It's really not much at all. And if you're at home, then I can have you also do an activity maybe with some tinfoil. If you've got aluminum or tinfoil at the house, But I gotta go. I'll see y'all later. You have a wonderful rest of your day, and bye bye.